Hi everyone, welcome to PyTexas 2020. My name is Paul Ganssle. I'm a software engineer and a contributor to many open source projects. Among other things, I'm a core developer of Python and a maintainer of dateutil and setuptools. As someone who primarily develops libraries, I'm obviously a fan of shared code, but I recognize that there are risks to taking on dependencies, whether they're third party or within your own organization. And the topic of this talk today is one of those risks, which is when something you depend on has a bug or any other incompatibility, it's obviously not as easy to fix as it would be if you were fixing a bug in your own code. Before we get started, though, I want to give you a warning. So this talk deals with a number of strategies for handling this situation, but it's organized as a series of strategic retreats away from what I would consider the right thing to do, right? While I've used each of these strategies in the past, they're mostly a collection of least bad options, and each strategy is, I think, a little bit worse than the last. So we will, of course, start with the right tool for the job, but as we move along, it'll get increasingly hacky and dangerous. Okay, so what do we mean by a bug in someone else's code? Here's an example that I recently encountered at work. This is a minimal working example, and the idea is that normally we could take this data frame and we could use the ag function. And what the ag function does is that it takes as arguments a function and then an axis and then any number of positional or keyword arguments. And what it does is it applies that function to either the rows or the columns of the data frame, basically calling the function with each row and then passing all additional arguments that are passed to dataframe.ag on each call to the function, right? So the way this should work is it should call f on our first row, and it should pass that to f, the row, and then the number 3. But if we run this with pandas version 1.1.3, it fails with some sort of thing about getting inconsistent arguments. It's getting two values for the argument axis. And if you change 3 from a positional argument to a keyword argument, it seems to work. So that's weird. Let's check the documentation. As you can see, the documentation does say that we should be able to pass positional arguments to it. So this is obviously not my bug, right? This is a bug in pandas. So what do we do about that? Well, the right thing to do, which is definitely where we should start, is to file an issue upstream, right? They can't fix the bug unless they know about it. So I put a minimal reproducer there and tell them the expected results. We can also try and fix it. In this case, it was easy enough for me to fix, so I submitted a patch and submitted a pull request. And in fact, this was straightforward enough to review that within a couple of days, it got merged. And so far, this is looking like a great open source success story. So what do I have to do next? I just have to wait for a release and then update my version, right? So within a month, I'll be able to have this new version of Pandas that has my bug fix. So what could go wrong? Well, for one thing, I might have production deadlines that are a little bit shorter than 1 month. If I have something that needs to get out next week, and it's affected by this bug, I don't have time to wait for a new release. And also there are maybe I do have a month, but there are some projects where the release cycle is quite long. Python actually just shortened its release cycle from being 18 months to 1 year. But even still, if you are relying on a new feature from Python, you're going to have to wait a year before it even gets released. And then you have to wait for your in-house deployment cycle, right? If you're using some stable Linux distro or, long-term support, it may be months or weeks or years, even internal, sort of faster moving systems, can take quite a long time to get through testing and QA and check for compatibility with all the packages you deploy. So if you have a problem now, and you need it fixed right away, what are you supposed to do? Well, you can start with a one-off workaround, right? In this case, it's pretty easy to just change our positional argument to a keyword argument. And in this case, we're also pretty indifferent to it, right? So I put a to-do comment here, but it's not even necessarily true that we need a to-do comment. If it was a little more hacky, I would want a to-do comment that says, hey, please clean this up when something changes. But in this case, it's not a big deal. And this works well if you only hit the bug in one place, or if the workaround is very simple. But if you're hitting it a lot, or it gets a little more complicated, you may want a wrapper function. So a wrapper function is basically something where you sort of mimic the function that has the bug in it, and then you encapsulate in that whatever workaround logic you need. So in this case, I've implemented dataframe_ag as a wrapper around df.ag, and then we just detect whether someone is passing positional arguments. And if so, I eagerly bind them to the function before I pass it to df.ag, right? I'm just closing over these original arguments so that df.ag never has to pass anything except keyword arguments. Right? So this is nice because it encapsulates the workaround logic. I don't have to re-implement this anywhere. And it also provides an easy target for later removal, right? All I have to do is search and replace dataframe_ag with df.ag or something like that. And then all of my call sites get fixed once the bug is fixed upstream. But we can say that we're going to clean up that tech debt later, but how often does that really happen, right? So generally, I like to assume that these sorts of hacks are going to be a little bit more long-lived than I would hope, and try and minimize the scope by building in an expiration, if possible, one that detects at runtime whether we even need the hack. And I call this opportunistic upgrading. I don't know if other people call it something different. The way it works is, we can take our original function, and all we have to do is we have to add in this little thing that says, oh, actually only do this binding trick if we're affected by the pandas bug, right? So our hack is only triggered if we would otherwise have hit the bug, which is great, right? It's minimal in scope. So how do we write that has pandas bug? Well, there's two ways to write this function, or two general strategies. One is to use feature detection. In this case, what we can do, we can detect, sometimes the missing feature is like an attribute or a function that either exists or doesn't exist. In this case, it's a bug, and the minimal reproducer is easy enough that I can just write a little function that tries to hit the bug deliberately, and if it does hit the bug, return true, otherwise return false. You can also use version checking. In this case, I happen to know the first version that's affected by the bug, and I also know the first version that's going to be released that isn't affected by the bug. So I can just write this function by looking at the version of pandas we have and checking if it's in the acceptable range. We can also improve on this a little bit by, instead of including the opportunistic upgrading in the wrapper function itself, is to only define the wrapper function if we would hit the bug, right? So here, if we're affected by the bug, we write our wrapper function. Otherwise, we just directly pass through, and dataframe_ag is just an alias for pd.dataframe.ag. This is nice because it really serves to minimize the scope of your hack, and it also minimizes the overhead, right? You don't have any additional function calling or anything going on in there. So I tend to do this pretty much all the time whenever it's ergonomic to do it, or whenever it's cheap to check for the existence of the bug. Okay, so real life examples. Most of the real life examples that I see that continue to exist are not backports of bug fixes, which is essentially what we're doing in our pandas example, but backports of features. So 6 is probably the most famous example. It's one of the most popular libraries on PyPI, and it's just used to allow you to opportunistically upgrade to use Python 3 features and to just write code that works for both Python 2 and Python 3. I have a couple of other examples here that you can check the slides for. They're pretty much just various kinds of backports, and you can check the code there if you want to see exactly how they're implemented. Okay, so that brings us to the next strategy. And this is where we start getting into sort of properly dangerous and hacky territory. And this strategy is monkey patching. So the idea behind monkey patching is that most modules and classes in Python are mutable, and they also live in a global namespace. So you can actually just dynamically modify any of the code that you would want to patch at runtime instead of applying a patch to the source code. So here's an example where we've decided that the abs method is sort of stodgy and flat, and it's just always returning positive numbers. We would like it to sort of embrace chaos and to shake things up. So what we've done is we've written our own version of abs called sixpack that 20% of the time will just return a negative number. And then if we assign dunder built-in.abs to be our sixpack function, whenever anyone calls abs, they'll actually be calling sixpack. And you can see that works. We sometimes get negative numbers when we call abs3. And this affects not just us, but it affects anyone using the namespace. So the fractions module uses abs in its hash. And so once we've patched it this way, you sometimes will, for the same fraction object, get a different hash. Right. So obviously it's cool that we can break the hash of fraction objects. But how does it actually help us fix bugs? Well, if we go back to our pandas example, you can see that we could take our wrapper function, and instead of making everyone call it, we can actually just patch it directly onto pd.dataframe. And that will just sort of globally and transparently fix the issue for all future callers. This is nice because it allows you to really to make it so you only have to change the code in one place when you're ready to remove your patch. You just have to remove the monkey patch. You don't have to change all the call sites to remove their wrapper functions. And it also is mostly helpful when you're trying to fix an issue in other code that you don't control, right? So if you're calling one of your dependencies, which in turn calls dataframe.ag using positional arguments, and that's suddenly breaking, if you monkey patch pandas.dataframe.ag, that will fix the issue. And obviously, you don't want to, you're not able to replace third-party code's function calls with your wrapper functions, and you wouldn't want to do that anyway. So that's kind of the benefit. But why is this a terrible idea? Because from here on out, pretty much all of it is terrible ideas. Well, the biggest problem is that code that uses this is hard to reason about, right? It has action at a distance. The values or the things that happen when you call a given function depend on which things have monkey patched what, and they may depend on things that have nothing to do with your code, right? Also, no one is expecting you to do this, right? They may be expecting to get the original function, and maybe your code has some slightly different properties that will start breaking things. And also, in order for monkey patching to be useful, it tends to be tightly coupled to implementation details. So, you're often not patching something like dataframe.ag. You're often patching something like dataframe._aggregate or some other private implementation detail. And that sort of thing doesn't survive well version upgrades, and it doesn't work very well when you're trying to support using your module with different versions of your dependencies. So if you do decide to do this, it's important to scope your patch correctly. So here's an example where we have two modules that appear to do the exact same thing, right? They just expose a function that returns pi/2. And if we decide that we want to patch math.pi so that pi is no longer 3.141 whatever, and is instead exactly 3, we can do that. And if you note, the first module actually works, right? Pi/2 is now 1.5. That's great. The second module, though, didn't get the monkey patch. Why is that? Well, the reason is that your first module, pi module, imports math, so it holds a reference to the global math module, and then it looks up the value of pi in the math namespace every time you call that function. Whereas pi module 2 looks up the value of pi on math at import time, and then it uses the saved value every time you call pi/2, right? So here we import pymodule2, that resolves this py to our 3.141 object. And then later when we patch math.py, the pymodule2 is unaffected, but pymodule isn't. If we want to fix this, we actually have to patch py in the pymodule2 namespace. So this is another one of those implementation details that you may be tightly coupled to. You have to make sure that you're patching the functions and the attributes and stuff that you need to use in the places where they're actually used, which can cause some inconsistencies and other problems. Okay, one other way you can scope as tightly as possible is that if you only need your patch to be active while you're calling certain functions, you can use a context manager, which will allow you to scope your patch to either just the body of the context manager or just to a function, right? So if you use this handy function from the standard library, context-lib.context manager, you can have it apply your patch, execute the body of either the function or the context, and then undo the patch. And this will automatically just work both as a context manager and as a decorator. So that's a helpful tip there. All right. Real-life examples. Probably the most prominent real-life example that you would see this being used at is setuptools, which extensively patches distutils whenever you import it. It's implemented a bunch of its bug fixes and some of its features as changes to the standard library distutils module. And at some point, pip started importing setuptools automatically before running setup.py so that it would be able to take advantage of some of the fixes that setuptools is applying to distutils. This was, I guess, expedient at the time, but it has made a lot of people start relying on this setuptools patch distutils, which has made it very difficult for setuptools to unravel this monkey patching, which it's been trying to do for years now. Okay, well, that moves us on to our next strategy, which is vendoring. So what is vendoring? Well, Webster's dictionary defines vendoring as the word you've entered isn't in the dictionary. But that's just because the fat cats at the dictionary don't want you to know that vendoring is actually the practice of including your dependencies directly in your project source tree. I don't know. I'm not sure exactly why the dictionary has decided to censor this word, but I'm on to you, Merriam-Webster. All right, so how do we achieve this? Well, basically, you just take the source code of something you want to include in your project, and then you put it under your project tree somewhere. Usually, you would put it under myproject._vendored, and then you would update all your references to the project to refer to the vendored version. So if you're trying to vendor squalene, you just go, just some package called squalene. That's not a real package. You just take all your statements that say import squalene and change them to import myproject._vendored.squalene. And then, of course, you would apply any patches to your local copy of squalene that you want, if that's why you're vendoring this. So the advantages here is that this sort of pins your dependency, so you don't have to worry if upstream changes or if your users may have globally installed different versions of the module. Your potentially fragile hack will not be affected by that. Of course, it means you're pinned to a specific dependency, and there may be breakage when you try and upgrade the dependency you're pinned at. It's also nice that this is scoped to your package only, right? It doesn't modify any globals. No one else has to reason about it. It's fairly self-contained. And probably the biggest use for this kind of thing is that it allows two packages to use otherwise incompatible versions of a shared dependency. So if I have a package A and B that I depend on, and A depends on B and has a maximum version of 1, but I depend on version 2 or more of B, then what I can do is I can vendor B directly into my source tree and use B version 2.0, while globally B version 1.0 is installed to satisfy A's dependency. And then I can do that while I hopefully wait for A to become compatible with version 2 of B. All right, so if we decide to do vendoring, two of the most common issues that arise when you're vendoring these things are sort of related, and they're worth keeping in mind. The first is that when there's two or more copies of any module existing in your runtime, it may have incompatibilities that you may not have anticipated. So, for example, most classes implement their comparison operations in terms of comparisons to objects of the same class. But if you have more than one copy of the same module in your runtime, even if they're the exact same version, you still have two different implementations of that class, and they aren't considered the same object for the purposes of isInstance or is or anything like that. So comparisons between vendored and non-vendored versions of the instances of the classes won't be able to compare to one another. And this is compounded by the next issue, which is that references to the package's top level name, even within the vendored package, will still hit the global package. So if you have something that is sometimes using absolute imports and importing squalene.magnitude, and sometimes using relative imports, they're just importing from .magnitude, you can come across a situation where this magnitude is coming from the global package, and this instance of a magnitude is coming from the local package, the vendored package. And if we ever hit the code path that compares this object to this one, we're going to get a type error. And to solve this, your options are pretty much all bad, right? They either involve extensively patching the local source to make sure that it has no references to the global module, or doing some sort of dark wizardry to get the namespaces to resolve correctly and to get imports to work correctly and things like that. So, pretty much, we're starting to see some downsides, right? Which is that it's a little hard to implement. It can be hard to maintain, not least of which because it complicates your build and your packaging, which is, often one of the harder things to do when you're doing Python deployments. It also has a tendency to be leaky in one way or the other. The import system was really not designed for you to have two versions of the same module importable. In some sense, this is not terribly different from, just having your own implementation of the library, but it's fairly easy to conflate in your mind the idea that you have a version of that package, even if it's vendored. So, and of course, this doesn't work very well for any dependency that's part of the public API, right? You can't be returning objects that are references to your own vendored versions. You can't be returning myproject._vendored.squalene magnitude objects, especially if people are going to have their own squalene magnitudes to compare things to. All right, so now that brings us to the real life examples. One of the real life examples is actually this talk. So to make it easier to deploy this talk, I vendor my only two dependencies, which are reveal.js and gecko reveal.js. And in fact, this talk specifically carries a patch in gecko reveal because I found a bug in gecko reveal right before it was time to record the talk. And because I'm a procrastinator, I obviously didn't have enough time to get it upstreamed. So hopefully I'll be able to get it upstreamed later. If you want some examples of Python packages that use vendoring, there's pip and setuptools. And then there's also invoke, and you can check their implementations to see. I think they each do it a little bit differently, both resolving the namespaces and doing the actual vendoring. All right. So the last option is deploying and maintaining a patch version of the library in your production distribution. So the difference with vendoring is that this is global rather than local to your package. So what you would do here is that you would take your patch version and you would either deploy it in whatever your production distribution is, whether that's a Linux-like distribution or you have a mirror of PyPI and you can put some patched wheels and tarballs up there, or you have a mono repo and you checked in a patched version. Unfortunately, in my experience, people take this not as their last option, but as their first option, because patching your local version is relatively easy to do, and the cost kind of only comes into play later on when you end up not being able to remove those patches. So the way it's usually accomplished is using patch files. So what you do is you store the original code as a tarball or as a folder or something, and then you store next to it some patches. And when you apply those patches, it gives you it's either that you store the original code and the patches, and then you apply the patches as part of build, or you store the patch version and the patches, and then you can undo the patches if you want to see the original code. This is helpful because it gives you a record of everything that you're changing, and to the extent that the patches will still cleanly apply to new versions, it might be easier to reduce friction when doing upgrades. A lot of people use this software called Quilt for generating and managing those patches. I don't really have time to go into it, but this link here is written by an expert, and it seems like a fairly good explanation of how Quilt works, and it will do a much better job than I could in the 30 seconds or so I have to cover this concept. Okay. And if you have very simple patches, and hopefully you do keep your patches very simple, you may even be able to accomplish this without any sort of patch management software or anything, just by adding a little rule in your makefile that uses sed or some other little scripting language. Obviously, if that gets too complicated, it's much worse than maintaining patches. But for something simple like search and replace of the path to a file, it seems fairly easy. And this seems to be an idiom that's common in the Arch Linux world, where they have a pretty strong cultural norm against patching upstream sources. Okay, so we've already started on the downsides, but I really want to hammer these home because I think this is the most tempting of the options. What you're doing here is you're basically maintaining a fork that upstream doesn't know about. For small patches, it may seem like you're like, oh, I just carry a couple patches. But the issue is that, the best case scenario is that upstream just steps on your patches and you have to redo your patches every once in a while. The worst case scenario is that you make some choices that are just fundamentally incompatible with the way that upstream is moving. And other people in your organization have come to rely on those choices, right? So that ends up adding friction to your upgrade process, and it may prevent you from upgrading at all. And your minor patches end up, in the end, becoming a proper full-on fork, and you have to maintain all the new features, and you can't really cleanly get patches from upstream. And then, of course, as time goes on, there's there's less guarantee of compatibility, right? If other third-party packages are using the package that you're patching, they can't test against your patch version, right? They test against upstream's version. So as time goes on, as you're carrying more and more patches, they are less and less likely to be compatible, and you can get yourself into a sort of tangled morass that's very hard to get out of. Okay, so I barely really even need to talk about the real-life examples. Pretty much every Linux distro does something like this, and most big companies do as well. There are some generally good reasons to do this, right? If you're just adjusting the package to work for your build system, that's something that you would obviously not want to go in upstream. And there are certain changes that are minimal enough, and maybe you tell upstream about them, that it's worth maintaining a small fork. But generally, you want to minimize the use of this strategy. Okay, well, that's it for all the strategies. I thought I would leave you with a couple of final thoughts. The first is that it's very easy to overlook the value of patience. Each of these strategies involves incurring some technical debt just as an expedient to get things moving faster. But you may want to consider reflecting on, if you're using these strategies a lot, or if you really feel the need for them, is there anything about your process that would allow you to develop strategies to patiently wait for upstream fixes to deploy, or at least to minimize the extent to which you are deviating from what upstream is doing. And then also, I think there's a tendency to start patching things and then say, well, in for a penny, in for a pound, right? We started patching things, and so we may as well just add our own features to things. But really, this is technical debt, right? You should be glad that you're only in for a penny and not in for a whole pound. You should accrue it thoughtfully and pay it down as quickly as possible. Okay, well, that's my talk. thank you so much for watching, and I hope you enjoy the rest of the conference.